Okay, what we want to talk about this afternoon for a little bit is spanning tree, STP, managing the spanning tree protocol. And the big sign there, what's its purpose? And its whole purpose is to stop layer 2 loops. We're going to talk about the basics, configuring, and troubleshooting STP. Before we start, would like to, I think, take a look at, if I can find the 101, what we mean by what goes on here. Now I'll take a look at some header information. But right now, these guys are all together. They don't have spanning tree running on them. So let me plug these two machines in, and let's see if we can cause a mess. Let's see. Well, I would have configured some that don't have IP addresses, huh? Well, we can fix that real quick. Put some IP addresses on these guys. 192.168.1.2. Already I'm starting to get a mess here because it's slowing itself down. What happens is, let's see, 192.168.1.3 is, since we don't have any mechanism to stop things, we just create a broadcast storm. Let's see if we can get to the other guy. P 92.168.1.3, and sometimes it goes and sometimes it doesn't go. But what you'll notice here is we're timed out, and as long as I got the addresses right, there's no reason it should time out because we're switch to switch arrangement here. Yeah, I didn't do that. A lot of times I get these 1.2 and 1.2 and 1.3, so 192.168, yeah. So what we have here is a situation that when a frame goes out to an unknown address, let's see if we can make a mess out of all of this. Then what happens to it? And if we follow this thing around, frame comes in and it's going to this address over here, unknown address. So it gets flooded out each of the ports. It gets here, still an unknown frame, gets flooded out all of the ports. Here an unknown frame gets flooded out all of the ports. Well, finally we're going to get an answer here to go back. But and then this one comes in, flooded out. This one, unknown, lots of different timings on these things. Unknown comes in here, flooded out all of the ports. And so we get a situation to where we just have frames going everywhere. What we have to do, and what spanning tree does for us, is to shut down one of the ports. Not really shut down as in shut down, but block one of the ports. Let's go in here and enable spanning tree on these guys. And if I do a show of spanning tree, it's going to tell me there are no instances. Show spanning tree, no spanning tree instances exist. Let's go to config T, spanning tree, and then we have to specify the VLAN. And the VLAN is one, it's the only one that's on here now. Priority route, we're going to, now we should be able to enable it. Let's see. Spanning. Well, I guess if I went to config, I'm in config. Spanning tree, VLAN 100. So that should have turned it on. Show spanning tree, and it still says that we have No instances of spanning tree. There's no big T. No. Wait, I got it, I think. No spanning tree. VLAN 1. And I think that's the only one that I have. Spanning tree. VLAN 1. Do show. Spanning tree. Well, now we've got it. Then we have some of these things here. We got listen, listen, and block, and we'll look at those. I think I didn't give it a VLAN, didn't I? So what I did earlier, you have to specify the VLANs because we're getting down to, and this one is a per VLAN spanning tree protocol. Spanning tree VLAN 1. Do show spanning tree. So it is starting up, and we have these in amber. They're in mode that they're trying to figure out a loop-free topology. Let's see, spanning tree VLAN 1. So now we're going to have, and it takes a little less than a minute for this to happen. We're going to look at how to configure it to operate a little bit faster. But when it gets done, we should have one of the ports that's going to be in blocked mode, in blocking mode. And a lot of what this lesson is about is how to make spanning tree work for us instead of us to work for it. So now we're here. We have one port that is blocked, and with that, I don't have my issue here anymore. Instantly go, because I don't have the loop. We break the physical loop so that we can continue to operate within the system. So spanning tree stops layer 2 loops, and that's exactly what it does. Basics, configure and troubleshoot. What we have to do is to, and I had a guy one time say, I want to know how to do a little more configuration of spanning tree. Well, not a whole lot of configuration to do. We can, and we're going to find out, we're going to have this root bridge, and it's going to be the one device that we have a loop-free topology to. And other than specifying it, it kind of takes care of itself. We can change some priorities, but what we're doing is trying to dictate which of the devices is going to be the device that everybody's going to. This does work. Story, and I know probably tired of the stories, but had an instructor in Roanoke who was a Cisco guy. He actually wound up being a co-author of one of their switch books. But he had put in, or at least helped put in, I don't know if he was lead on it or what, a network in Chicago for a big organization, and he never said who it was. I think it was a mutual fund or something like that. And they elected not to use spanning tree on their network. That it takes too much going on with it, and it is it is a broadcast protocol. It has a lot of traffic going on. It sends traffic back and forth. It's trying to determine if there's a loop-free topology. And remember, one of the troubleshootings that we had last time was that too many topology changes, the network goes down a little bit every once for occasionally. But what had happened to this organization is their network went down completely. And they called him and flew him to Chicago. And he said he walked into the NOC and looked at the patch panel and moved one wire. And when he moved one wire, the network was back in came back. It takes a little while for this to happen. We had this was during the hub days, so there wasn't any spanning tree on hubs. But at night class, I guess that somebody got tired of being there or something. They kind of knew what would happen. So they had plugged one port of a hub into the other port of the hub, creating a loop. And it eventually brought down the network. I was doing day classes, and when I came in, the guy that was the network administrator at the time said, the router's broke. Router's not working. The router's broke. Walked into the room where I was supposed to teach, and all of the lights on the hub were lit up. And then look a little closer, and here's a wire going out one port and in the other port. Take it out. Then it started settling down. It took about 2 hours for the network to settle down. So those things will happen to you. There are protocols available to help mitigate what goes on the networks, and it's a matter of whether you want to configure it, whether you don't want to configure it. Again, the Chicago company, they don't want to configure it because they said it takes too much bandwidth. It doesn't really take a lot of bandwidth. There is a lot of activity goes on with it, but not a lot of bandwidth with it. And I said that we would look at a frame. Let's see, I get bar chart going here. And one of the differences between layer 2 and layer 3 is the TTL, the time to live. That is in the layer 3 data. There are some STP, spanning tree protocol, STP bridges, and you see there's a bunch of it that goes on here. Frame, IEEE, destination, spanning tree for bridges, and then 0, 1, the source and destination, the destination spanning tree for bridges, and then the source address. This device, and I don't even remember this particular router, but I obviously had it. LLC, link layer, logical link control, and spanning tree BPDUs. So we have the spanning tree BPDUs, the spanning tree protocol. Lots of things going on here. BPDU configuration, BPDU flags, and this is not a whole lot in it. Topology change, acknowledgement, topology change. So we got an acknowledgement and a topology change. Do we acknowledge it, or was there a topology change? And that's what's in it. The root identifier, and we'll talk about the root bridge here in a second. Hello time, forward delay, the things that are going on. But that's not why we came here. And we talked about ARP, and we didn't really do anything. But when we send an ARP, it goes to broadcast, and what it says: address resolution protocol, sender 192.168.100.165, target MAC address, which is any, target IP address 192.168.100.1, and then here somewhere it says that ARP who has 192.168.100.1 tell 192.168 whatever that address was, and it didn't go crazy, didn't it? Yeah, I lost the ARP. There's an ARP. Who has these addresses? I'm not going to see their replies because the ARP replies are unicast and not multicast. But what we're going to look at here quickly, I hope, is a TCP Ether frame layer 2 destination source. We don't have any mechanism to stop these loops. When I go into IP, I'm going to go down here, TCP destination. This is the differentiated services field, the things like that. Flags here. Oh, I have a time to live, a TTL, and this one is 128. And all of them are going to be a little bit different. But TTL 128, that's a lot of routers, but it's eventually going to go away. You can create a loop. It's kind of neat to create a loop. You can see it going back and forth, back and forth, back and forth. And then whenever the TTL is exceeded, you get an error message back that the packet died en route. TCP to destination, and notice here we talk about that each layer and the layer above and all that stuff. Protocol TCP 6, and this is at layer 3. It means the next protocol is TCP. So we can see those things that goes on. The layer 3 TTL, the time to live, is what keeps us from having billions, trillions, gazillions, undecillion of frames or data packets, not frames, but data packets running around on the internet that couldn't find a home. So if they can't find a home, get an error message and it gets dropped. So back to the basics, the configuring. Spanning tree achieves its primary objective of preventing network loops at layer 2. On bridges or switches, bridges and switches, a bridge is the original kind of device that was their incarnation of the device, and that's not the right word either. Switches came along later, and switches were called at one time multi-port bridges. There is a difference between switch and bridges. The bridges work in software, and the switches work in hardware. So what did a bridge actually do? And this was in some of the really old devices. If we had our piece of coax here with all of our machines on it, and we had our piece of coax here with all of our machines on it, what it really did in a bridge is something like that. It had a MAC address table, and it would have the MAC addresses of the devices on each side of the links. And if I was going from A to B here, and since we have the CSMA carrier sense multiple access, it would come down to this point and check its MAC table and say, oh, B's not over here. B is not over here, so I'm not going to send the traffic over here. So this was the bridge was the first attempt to minimize the amount of traffic in a collision domain that we kind of use. So monitoring bridges and switches to track all the links and shut down the redundant ones. We want to have a single path to these devices. Uses the spanning tree algorithm. First, it's going to create a topology database and then search out, disable the redundant links. And when spanning tree with spanning tree running, the frames will only be forwarded out only on premium STP chosen links. Premium STP chosen. Premium links are the ones that are going to go someplace. The ones that are not going to be redundant links. Switching loop we just looked at. It's a great protocol to use in networks like the one shown below, or like a lot of different networks. Let me show you some other kind of places that we might use it. Or actually, after I closed down the one that I didn't mean to. That will open packet tracer, I hope. And see if I can find the one that I want. Of course not. I do have one's got a bunch of, I hope, examples on it. Yeah. Spanning tree, all sorts of different topologies, the way we connect networks together that we might use, and it'll take these things again a few minutes to sort out. The numbers here represent the cost. Each link is going to have a cost, and that's going to be based upon the speed. So in this one, the 19s are going to be the 100 megs, and the 4s are going to be gigabit connections. And we're going to, and all of a sudden they're all working now. Huh? So this one, loop-free topology, we have two different connections that are turned off, and here we have two different connections that are turned off. So what the protocol is trying to do is to again have a loop-free topology to this thing called a root bridge, which we are going to get to the election of in just a couple of minutes. So to using these things, a switch network with a redundant topology includes switching loops without some type of layer 2 mechanism. Hopefully saw that in the demo. Without some type of mechanism, we're going to be in trouble, because we're going to get into a loop, a layer 2 storm, broadcast storm that goes on. Issues of broadcast storms, multiple frame copies, and MAC table thrashing. MAC table thrashing is it keeps changing the place that the frame came in, the port that it came in on. First it would be one, and then it would be the other. It came back. It's going to go two different paths. Okay, this one says, oh yeah, this is where this port, this MAC address is. This one, this is where the MAC address is. Both of them, same thing. And then we come back to this switch here. It now has that MAC address on two locations. So it's going to change the location of the MAC address based on whoever got there last when we do those things. With spanning tree, like the example, one of the ports is going to be blocked to prevent those loops, so that there's only a single path that goes on. The switches themselves have this thing called a bridge ID, which is going to it's going to identify them, obviously, and it's going to establish a priority. It's going to establish the priority, the number, the string of characters, the string of numbers that's going to be used in the election of the root bridge. The downside of the way this thing works is switches generally are going to use the lower of, routers are generally going to use the higher of. So the bridge ID, if you look here, the bridge ID is an 8-bit value unique to the switch at the top there, a 2-byte priority field, and a 6-byte system ID. Unique, consistent. The priority is by 32768 by default, and the 6-byte system ID is going to be the MAC address. So what we have, that by default all of them have a priority of 32768. And they're all going to have different MAC addresses. So what we're going to wind up with, unless we do some configuration, is the switch that's probably going to be the oldest and the least capable, because it's going to be the one with the lowest MAC address. So the bridge ID elects the root bridge in the STP domain to determine the root port for each of the remaining devices when there's more than one potential root port available, because they have equal cost. The root port is the port that it goes out, the frame goes out to get to the root bridge. So lots of terms here. We have root bridge, loop-free path to the loop bridge, root port, the port that it goes out of to get to the root bridge, designated port, term that's not been introduced yet, the port that the root port connects to. The key bridge ID is 8 bytes long, includes both the priority and MAC address as illustrated in the figure. So we have here the bridge priority 0 to 65,535, 32768 is the default, and the MAC address. We say that it's actually going to be the this, the 32768 plus whatever the VLAN number is. But since if we did it that way, VLAN 1, everything gets 1 added to it. It's still going to be the one with the lowest MAC address. All of those being equal. 3 kinds of BPDUs, Bridge Protocol Data Units. Configuration used by SpanningTree to provide the information, a topology change, and an acknowledgement of BPDU. And we saw in the frame on Wireshark the topology change BPDU to tell switches that there has been a topology change, and then the acknowledgement to acknowledge the BPDU change. So let's see, one more, and then I want to do a little demo here. Actually, I want to do a little demo, and then we'll do some more of these slides. I have, guess what, a demo that I want to look at here. And this is a flash which is in the shared material. I'll allow the blocked content, I think, and we'll start this thing. We're going to have the 3, and it says bridges, bridge, switch, think of them, and we're going to connect them together in the triangle like we had before. And if you notice that each of them has a bridge ID 32768, 32768, 32768. The MAC addresses are really big ones, 1, 2, and 3. So when these guys each has a connection to the other bridges, when they start up, all the bridges think that they are going to be, that they are the root bridge. So they're going to send out BPDUs and all claim to be root. The first step, bridge C sends a BPDU to bridges A and B, announcing that C is the root with the root ID 32768-2. Note that B's root ID will change from 3 to 2. So we're going to have C send its claim to be the root to all of the attached switches, bridges. Bridge ID, bridge and switch are used a lot simultaneously. A says, hey, mine's still lower, so I am root. B looks at this and says, my root ID is higher. C is root. So we just did that. Now, root, I am root. A says he's root. C is root. B says C is root because it's the only one he's got the BPDU from. And bridge C still thinks that it's the root bridge. The next step, bridge A to send the BPDU towards B and C. And when we do that, it's going to then kind of settle things here with this one over here, 1 to 2. My root ID is higher. A is root. A is the root bridge, and down here C is going to do the comparison. And hey, A is the root bridge. So my root ID is higher. A is the root. So we have established the root bridge. The next thing that we have to do is to block one of the ports to prevent this physical loop. Every non-root bridge must select one root port, and the root port is the one that goes toward the root bridge. So we have now decided that A here is the root bridge. So we have the root bridge, everything else is not, obviously. A bridge's root port is the port closest to the root bridge. That's kind of, to me, okay, closest to, electrically closest to, data-wise closest to. It's the one that goes towards the root bridge. So the root port, regardless of where it is going to go toward the root bridge. Assuming that all the links have the same speed, 100 meg, so each of the costs is going to be 19, and this is the according to IEEE. So bridges B and C will elect their root ports, and we're going to have costs here of, actually I guess we could put the cost here of 19 on each of these, 19, 19, and 19. So it makes sense. The closest to the least cost we're going to be 19, and the least cost is going to be 19. So these are going to be the root ports. Now we have to determine which of these two ports are going to be the blocked port, because we need to block one of the ports in order to have the loop-free topology. The bridge containing the designated port for a given segment is referred to as a designated bridge for that segment. Okay, there are three segments: segment 1, segment 2, and segment 3. The path cost to the root bridge is the same for bridges B and C. The tiebreaker is the lower bridge ID of bridge C. So the path cost to the root bridge is the same for bridge B and bridge C. The tiebreaker is the lower bridge ID of bridge C. So when we look at it, it has the lower bridge ID over here. So the lower again wins. So we're going to have our designated port here, and are going to have our blocked port here. The higher bridge ID is going to have the blocked port. So again, bridges generally, no absolutes on anything, but generally in bridges, the lower is going to win in these things. The lower MAC address, if we had multiple ports, be the lower port number, will do those things. And this one is going to become the block port. So the simple how this thing works, how do we get to the root bridge, how do we determine which of the ports is going to be in blocking state and which are going to be in forwarding state. And again, we have designated ports and root ports. The root port is the path to the root bridge, and the root bridge, on the root bridge, all of the ports would then be designated ports, and that's one of the things that's going to distinguish a root bridge, is all of the ports are going to be up on it. STP is 802.1d bridge and layer 2 management protocol, prevents the undesirable links. Can only be one existing active path between two stations for the proper functioning. And STP is transparent to the end stations. The computers don't have any idea that STP spanning trees run. It's a switch protocol to manage the links, manage the topology, the layer 2 topology within the network. Root switch is the switch that has all of the ports in either designated role or backup role. The designated switch that has at least one of its ports in the designated role. And I'll look and see what I have here. I think that we're going to look at this a couple of times, but let's maybe take a look at some of what goes on here, looking at some of the configuration. On this one, and let's see if I can make it a little bigger so you can see the costs. Here, cost of 19 going in this direction. If we go in this direction, it's going to be 23. Cost in this direction of 8, here 4, and here 4. So it kind of makes sense as to who does what. When I look at the switch itself, and we show spanning tree, these are designated ports, designated, designated, designated. And this one up here says this bridge is root. Just happened to stumble across that one. This bridge is root. All of the ports are forwarding. So we have this bridge is the root for VLAN 1. So we have VLAN 1. It is the root bridge. What we could do, and let's see if I can make this work, since it is a VLAN 30, now we don't already have VLANs on here, don't we? VLAN 30, root ID priority, and address. It's not the root bridge for VLAN 30. So We have forwarding here on these things. Spanning tree, priority, address, cost. VLAN 20, and it's also not going to be the root bridge. So it is going to be the root bridge for VLAN 10. So we can look at, let's see how many VLAN are on here. Show VLAN, yeah, we do have the 10, 20, 30. So we have the gig 2 forwarding. We can, priority 32768, that's one of the things we want to look at. VLAN 30 here, this one has a priority of 24606. The lowest is going to win, and a priority here, the bridge SC. The root the priority of the root bridge is 24606. This one is 32798, which is 32768 plus the VLAN ID. So 32768 plus 30 gives us 32798. All of the VLAN 30 devices are going to have the 30 added to it. Sometimes we have forwarding to the other one, so we can look at it. Let's see. This one has everything up. Let's look and see what it's got. Show spanning tree. So this guy shows spanning tree, VLAN 1, 32769, bridge ID 32769. So it's not the root bridge here. We have a designated. We have a root port going to a root bridge. So gig 01 is a root port for VLAN 1 here. When we go on down, 24, this one is just in a forwarding state. The costs of it, let's see, 20. Yeah, this bridge is root for VLAN 20. VLAN 30, we still haven't found its root port yet, have we? VLAN 30, 24606, 32798, again for 30. So, any guesses on which one may be? All these others have ports blocked on them. Blocking is the term. Let's see what we got here. So, I don't know, so we're just looking at them. VLAN 30, this bridge is root for VLAN 30. So we now have identified the root bridges, and each of the VLANs have a different root bridge. What that can help us do is better utilize all of the ports instead of having all of them with the same root bridge and all of the traffic going through the same ports and all of the VLANs having the same block ports. What we can do with the per VLAN spanning tree, PVST, per VLAN spanning tree protocol, is have each of our VLANs to have a different root bridge, and that way we can better utilize the capabilities of the network itself, of the infrastructure that we have with it. So just a quick there. So STP 802.1d, the root switch is the switch that has all of its ports as either the designated role or as a backup role, and we'll look at those in a minute, those terms as we go through here. The designated switch that has at least one of its ports in the designated role. So the designated a root port goes to a designated port. Root port is the path towards the root bridge that we have. You say, oh, it's not such a big deal. But if you had something like this and you wanted to have physical redundancy, you would need something like spanning tree. Maybe you could sit out and calculate the loop-free topology for everything. I can't. But what it allows us to do is have physical backups without actually having logical backups. So that if something goes down, a switch goes down, a path goes down, a port goes down, the spanning tree protocol can do the calculations, the recalculations, and have a new loop-free path for everything and keep the network up. Does it go down for a few minutes, seconds? Yes. Does it go down and stay down like my friends did in Chicago? No. Port roles. The ports themselves, the spanning tree uses a spanning tree algorithm, we've said that, assigns a role to each port based on the role of the port in the topology. The roles, the root port, a forwarding port elected for the spanning tree topology. The root ports are the ports that go toward the root bridge. A designated port, you can say forwarding port elected for every switch LAN segment. Every root port connects to a designated port. And then we have alternate port. A block port provides an alternate path to the root bridge, and then a backup port, a block port used in a loopback configuration. I want to show a picture of what a backup and alternate. The backup is kind of the backup to the alternate port. When we look at these things in the backup, the designated port and the root port, we have the alternate port. The backup port here is if we have two of them down here connected to the same bus, is really what we have here. One of them is going to be an alternate maybe, and the other one is going to be a backup. So one of them is going to be on, one of them is going to be off. But we have two ports down here, and I guess that two ports down here that are operating here. One of them is on and one of them is going to be blocked. So we have one that's maybe the alternate, and the other one is going to be the backup port. The alternate, actually the alternate's over here, it says. The alternate port is one that is waiting to be used. So when we do those, the STP versus rapid spanning tree, and we haven't talked about rapid spanning tree, we will in a second. Spanning tree is the default. The default one on Cisco switches is per VLAN spanning tree protocol. Spanning tree itself, the real STP, only worked with ISL. And then we have per VLAN spanning tree on a per VLAN basis, and it worked with ISL. Per VLAN spanning tree plus works with 802.1q. So a new variable assigned to a bridge port in the spanning tree. In the port stage STP, we have a forwarding, which can be the root and the designated ports, and rapid root and designated ports. Blocking are just called blocked, and in rapid you call backup or alternate ports for the blocking state. And yes, we are going to go through how each of these states works here as we go through this thing. The modes, and I think I actually got that slide a little bit out of sequence. I didn't want the table quite yet, but the three modes supported by the newer Cisco switches are per VLAN spanning tree plus, rapid per VLAN spanning tree plus, and multiple spanning tree protocol. Default mode PVST plus, per VLAN spanning tree plus. It is 802.1d standard and Cisco proprietary extensions. This mode is based upon 802.1d and the Cisco proprietary extension. It's the default for all of the Ethernet port-based VLANs on the Cisco switches. Rapid per VLAN is the same as per VLAN, except it uses a rapid convergence, and we'll look at the timers it uses in a few minutes and why is it faster. Because it just works faster. Well, actually it does work faster, but it does some other things. Multiple spanning tree protocol says runs on top of the rapid based on the 802.1w standard. It is 802.1s. Rapid is 802.1w. So per VLAN 802.1d, rapid per VLAN 802.1w, multiple 802.1s. And it is associated, runs on top of rapid per VLAN. Multiple is if we had a whole bunch of VLANs, say that we had a couple thousand VLANs, or let's say we had 300 or 400 VLANs. Instead of having one instance for every VLAN, one spanning tree instance, which would take an awful lot of calculation, what multiple does is groups VLANs together. So VLAN 1 to 50 may be, maybe in spanning tree group, multiple spanning tree group 1, and then 51 to 100 may be in another one, and on down the line. So instead of having an instance for each of the VLANs, we have multiple VLANs associated with an instance. Reduces the calculation cost for the switches themselves, and as well as reduces the number of topology changes that you're going to see, the number of recalculations that have to take place in the VLAN. So the default here, per VLAN spanning tree plus, same functionality as per VLAN spanning tree, but it uses .1Q instead of ISL. So the plus is the thing that allows us to use 802.1Q, where we just had per VLAN, we just talk about spanning tree. When we refer to spanning tree today, we're talking about per VLAN spanning tree plus. An enhancement of the .1Q, not supported on non-Cisco devices. Single instance runs on each configured VLAN when it is not manually disabled, and you saw what happens when it's manually disabled with the demo. And the way that you disable it is use no spanning tree, VLAN, whatever. You would enable it and disable it on a per VLAN basis because it's a per VLAN protocol. Each VLAN running its own instance, unless we're using the multiple spanning tree, the MSTP protocol, where we group the VLANs together. Fault-tolerant networks, got to have a loop-free path, otherwise we're going to have a mess, a real mess, and if you have the capability to hook some switches up together, see what happens when you do something like that. We can shut down the network pretty quickly. STP algorithm calculates the best loop-free path throughout a switched network, and it uses that based upon the port costs. And we've seen a couple of them. 19 was 100 meg, and 4 was gig. As the speeds increase on the devices, the cost, the calculation costs are going to change. When they started using this, there was no such thing as a gigabit port. So 100 meg and a gig were the same, although 100 meg and a gig really aren't the same, as we know. So as the speeds change, as the hardware changes, the cost factor is going to change on these things. Don't forward frames, but use the frames to construct a loop-free path. They don't forward. They're just communicating with each other. They're hello packets. As you saw, we had acknowledgments. There's not a whole lot in one of these things. Rapid per VLAN 802.1W implemented is still a per VLAN rapid spanning tree protocol plus, which gives us the 802.1Q. Single instance runs on each VLAN, and each rapid per VLAN instance on a VLAN uses a single root switch. So each instance has a root switch, just like we had before. The rapid and the per VLANs are each instance a root switch. And if they're all not configured, they're all going to use, we have multiple VLANs, they're all going to use the same topology, which might not be what we want, because we might want to be able to use the capabilities to not have basically a port sitting there saying, oh, hey, somebody fail so I can work, somebody fail so I can come up, somebody fail so I can come up. So we have some resources doing nothing, and we really don't want to do those things. A version summary slide, and hopefully it helps a little bit. Doesn't confuse too much, because this came from a different presentation, but 802.11d, 802.11d the legacy standard of spanning tree when bridges were around, common spanning tree protocol. Then we went to the per VLAN spanning tree. The per VLAN only supported ISL, per VLAN spanning tree protocol plus ISL and 802.1q. The Cisco enhancement of the spanning tree that provides a separate 802.1d spanning tree instance. And if we have hundreds of VLANs, Cisco environments, hundreds of instances of spanning tree, you have the on route and the on route calculations. The 2 seconds here, the BPDUs are going to, and that's why these guys in Chicago didn't want it. The BPDUs are going to be every 2 seconds when we look at those things. The multiple spanning tree, multiple VLANs to the same spanning tree instance, multiple VLANs to a single spanning tree instance, 802.1s. 2 spanning tree instances over here, 1 to 100 and 101 to 200, instance 1 and 2 for the multiple, so that we group them together. We don't have the hundreds of calculations going around at the same time. Rapid improves the convergence over the 1998 version. The 1998 version, the per VLAN rolls to the ports and enhances the BPDU exchanges. It is much quicker to converge, and try to do a demo on that. Only supports a single instance of spanning tree, and I think that's a big deal. Single instance of spanning tree. Rapid convergence, 1 spanning tree instance per VLAN, but have rapid convergence for those things. Do this one and then take a break. When a switch powers up, it changes to rapid mode and broadcasts a special spanning tree message to all the ports with BPDU, and we saw what a BPDU looked like in the Wireshark. And this says rapid. It depends on how it's configured. If it's a default, it's going to be a per VLAN, PBST, not rapid PBST. Each configuration will contain the following information: a unique access point ID, and this is if it is a wireless access point. And again, they kind of drive me crazy sometimes, because we jump from switches to wireless access points. And we're really doing the same thing with these things. I want to open this thing back up. See if I can get the spanning tree back up so we can look at it when we're talking about these things. A unique ID, the cost of the spanning tree path to the root. Let's see, which one was that? TCP. Cost to the root, the sending access point ID, the age of the message, the sending interfaces, identifier values of the hello and the forward time and the max age. So let's go over here and look at one of these spanning trees and see if that is in fact the case. Spanning tree, 802 destination source, we have the length and the padding. The access points here, spanning tree BPDU, spanning tree BPDU, the control field, the spanning tree protocol. We have the protocol identifier. Let's see, we have the protocol version, the BPDU type, cost of the spanning tree to the root path cost. I'm just looking at the slide. The sending access points, access point ID, and that's for an access point, but we have the bridge identifier for these things. The age of the message age here, 0. Let's see, the values for the hello timer, max age timer, and the forward delay timer. So again, not a whole lot in here. And what we're advertising: the root identifier, the root bridge priority, the system ID, and the bridge system ID. So looking at cost to find out what is the best. And what really happens is they send a frame out, and it kind of goes around the world. If it comes back to you, then you know that there is a loop. All access points in the layer 2 that participate in STP gather the information about the other access points, and in exchange the BPDU data messages results in a unique spanning tree route for each spanning tree instance is elected. Each VLAN, each spanning tree instance, has a root bridge. A designated access point for every LAN segment is elected. The loops in the network are removed by blocking the layer 2 interfaces that are connected to redundant links. So instead of having a time to live, something that decrements and then we throw the data away, we block the port. And a topology change is if we plug something in and then we get a spanning tree message that there's been a topology change and acknowledge, and it has to go on down the line because if a switch fails, if we plug a wire in or unplug a wire to a port, it's going to stimulate some of the topology changes, and we don't really want to have all of that calculation going on unless it's absolutely necessary. And it is time for continuing with the root bridge selection. The process, the flow here, the lowest path cost, and the path cost, the two costs are up here. The cost after 2004 and after the cost to 1998 and before. You can see that we didn't even have before 1998, before we didn't have a 100 gig or we didn't have a terabyte to look at those things. And a 10 gig, the 1 gig, how much are the costs? Although if you'll notice, the ones that we're using in the problems, we're using the 1998 cost, the 19 for the 100 meg and the 4 for the gigabit. But the new costs are the ones on the far right. So as we increase the speeds, we got to change the cost because some of those things never happened before. And this is step through one of the processes, and let's see if I can get it here. I'll step through it for you, or try to when we do that. So we have these guys here, the gigabit. So we're going to have a cost of 4, a cost of 4, and a cost of 4. So nothing really big. Okay, I got my root bridge here, but let's look at it. 32.768, 32.768, 32.768. It really won't be that if you look at the priority in the show spanning tree. It's 32.768 plus the VLAN ID. The VLAN ID. This is what we would configure it with. You notice that it is in the most significant digits of the whole priority, concatenated, appended to, or put together with, combined with the MAC address. So the MAC address and the priority are going to constitute the bridge priority. If we change this 32.768 to, I say, 24.600 or whatever, it's going to drive the whole thing down because it's in the most significant bit. So we can dictate by using the bridge priority, the priority of the bridge, and I'll look at one in a second. You can specify a priority, or you can just specify a route, and it'll set a priority for you. So the priority of these things. So what we would look at, since they're all 32.768, would be the MAC addresses. This one starts with 4 zeros. Well, it's going to be the lowest, obviously, because we have those 4 zeros. So this is going to be the lowest MAC. So then it is going to be the root bridge. The root ports are pretty obvious here. Now let's get back. We had the 4 and the 4 and the 4. So the root ports. This is going to be a root port. Now let me try that again. And let's use a different color here. This will be the root port. The root port goes towards the root bridge, and this will be the root port because they're the lowest cost, and that was the first thing we looked at, was the low cost. These up at the top are going to be designated ports. They're accepting information. What we then have to figure out over here is which one of these guys is going to be the blocked port. And it's going to be the one with the highest MAC address, because they're all 32.768. So we have a 0030 and a 000A. So this one should be a designated port, or not designated port, forwarding port, a forwarding port, and this one should be a block port, I think. Find all of the links that are going to work for it. And I think that the answer is on the next slide. Let's see how we did. We got the root port, the cost with the root ports, and then they call them forwarding ports, and they are forwarding ports, but they're also designated ports that work on these things. So then we have the forwarding port here, like we calculated, and the blocked port on the one with the higher MAC address to create our loop-free topology in this little network here. Multiple spanning tree is the one that groups the different VLANs together. Multiple spanning tree uses rapid RSTP, actually per VLAN, rapid spanning tree protocol. For rapid convergence, enables multiple VLANs to be grouped into and mapped to the same spanning tree instance, so that they're all going to use the same block port, all the ones that are grouped together. Fewer calculations, a lot less topology changes are going to be calculated that goes on with these things. Multiple forwarding paths for the data traffic, load balancing, reduces the number of instances to support a large number of VLANs, improves the fault tolerance because of failure in one instance. One forwarding path doesn't affect other instances, other forwarding paths. And that, I mean, if you think about it, we only have a certain number of paths that would be available. We could run into an instance that one of the spanning tree paths disabled a particular, blocked a particular port, which was being used by another instance of it. Optional features on these things, optional feature enhancing loop prevention, protecting against possible misconfiguration by users, and providing better control over the protocol parameters. PortFast and BPDU Guard are two of the tools that we want to look at. PortFast, what PortFast does basically says, don't worry about it. It's not a trunk port, it's an in port. Don't even use spanning tree. And I'll give you an instance. Been there, done that with that. We would have, in the room, we put in new Windows machines, and the new Windows machines by default allowed the operating system to take control of the NICs and shut down the NICs. So students would come in, the computers came on using a BIOS clock, turned them on at 6 o'clock, I think, and then when the students got in at 8, computers were up and running. Control-Alt-Delete, type in your username and password. Students type Control-Alt-Delete, username and password, and they get an error message back. Authentication server not available. Control-Alt-Delete, authentication server not available, which means they can't get to Active Directory. What was happening is that when they hit Control-Alt-Delete, they woke up the NIC, which then turned on the port on the switch. The switch then went into the spanning tree process, and it took 50 seconds, about a minute, and you'd be surprised how many times you can try till you put in your username and password and get that message back in 40 seconds, 50 seconds. And you know, it gets very frustrating. So the answer to that was PortFast. When we configured PortFast, as soon as the NIC came up, as soon as the NIC came on, it activated the port. So they're going to become edge ports when we do that. PortFast on all the access ports, not on trunk ports. The the edge ports, the in ports, where we're not going to have any of the devices connecting to something that could cause a loop, connecting to another switch. Listening and learning states, it goes directly from blocking to forwarding, and we haven't talked about the states yet, but we'll get them in just a second. But port fast causes the layer 2 LAN port configured as an access port to enter the forwarding state immediately by allowing the device to pass the listening and learning states. The process is going to be blocking, listening, learning. And again, we're going to have the timers laid out in a slide here in a few minutes as to why it takes so long to get these things going. Connected to a single workstation or a server should not receive BPDUs. They should not be getting the spanning tree. They don't need the spanning tree because they're not going to be able to create loops. They're not going to be able to have ports in a disabled state so that they can have the possibility of creating the backup paths that we use. It can enable on a port for immediate transition. Can be enabled on trunk ports and can have an operational value that is different from the configured value. We want these things to be on the I was trying to get this up, to be on the edge ports. So in this thing, and I don't think that we can turn this off and turn it back on, maybe. Not the switch, the computer. Oh, that was a switch. Let's do that. Let's try the computer here. And see if it goes through. It's going through the spanning tree process. And it's going to take about 50 seconds to do that. We can, on one port at a time, and we'll do that one here real quick, and it is Fast Ethernet 03. Or we could do a range. Interface Fast Ethernet 03. And we can do spanning tree port fast. And that's all we need to do. But we'll only have effect when the interface is in non-trunking mode. We could go in here and do switch. Well, let's just go ahead and see what happens when we do this thing. Let's turn this one off and on again. And it comes up immediately. It doesn't go through any of the spanning trees. So port fast will bring the ports up immediately. We could do them one at a time. We could do a range, but there is an easier way. We do spanning tree, port fast, default. Turn spanning tree on for all of the ports on our device. So what happens if we have a switch here, which we do? So it's not going to be an edge device. We don't want it to be an edge device because if something happens and then it creates a loop, we want the system to know that it creates a loop. Let's see if we can do a reload here and see what happens on this thing. See if it comes up immediately or not. And I'm hoping not. It's supposed to be not. And we're kind of going into a negotiation process here. What should happen is if we configure a switch to this device and it gets a BPDU, it goes into regular spanning tree negotiation process. And let's see if we can maybe see some of those port states here. I probably waited too long. So spanning tree, it's already in forwarding state. We'll look at some of those in a minute. One of the other things that we can do, so port fast brings the port ups immediately, says they're edge ports. They don't have anything to do with switches, with anything that can create a loop for us. But what if somebody were to plug in a switch and create a loop? And again, just the standard practice, it should be go into the regular negotiation process. The other thing that we can do is to enable BPDU guard. Balances the functionality of portfast. BPDU guard protection against layer 2 loops that SpanningTree can't provide when portfast is enabled. Layer 2 interfaces, the edge ports with valid configurations don't receive BPDUs. When BPDU guard is enabled on a port, it shuts down, puts in error disabled. A port that receives a BPDU. So let's see if we can make one of these guys shut down. Fast Ethernet, as I said, probably would work better if you could see it, wouldn't it? Fast Ethernet 05. Well, I guess you'll have to believe me that this is fast Ethernet. Well, let's just go with the gig 02. So let's go into interface gig 02 and do BP. Let's see. Configure interface. SpanningTree BPDU guard. And then we can have to enable it or disable it on the port. So we will enable it on this port and let's see what happens. Maybe if we probably do a reload on this one and watch it, well, it says that line protocol changed state to up, so let's do a reload. Let's see. Now it changed. Okay, now it did what it was supposed to. The BPDU happened. The BPDU happened and it shut down that port. That port should be in error disable mode. So if we look at it, show interface gig 02, I think, right? When we look at it, it's in error disable mode. It has an error that because we had portfast, but just in case somebody plugs a switch in on us and was able to create a loop, we put BPDU guard on it. BPDU guard shuts them down. If you don't have it enabled, what's supposed to happen when it gets a BPDU is it goes into a standard negotiation, spanning tree negotiation process to see if there actually has been a loop configured on this thing. So BPDU guards portfast, comes up immediately. BPDU guard shuts it down if it gets a BPDU and it's in portfast, and then SpanningTree negotiates to see if there are loops and blocks. Doesn't shut down, but blocks. I said shuts down. It actually, as you saw that one, it put into error disable mode, which is effectively shut down. Blocking is a state to where the port is waiting for another message. It says, hey, I need you now. So would you please get back into the game? It can be brought up a little bit faster. It's not in an actual shutdown mode. So BPDU guard can be configured globally, only effective on ports in the operational port fast stage. So we should be able to, and I know you're tired of seeing these things, but if we do that, can we enable it on SpanningTree globally? So what we could do, should be able to do, is to go in here and do SpanningTree. I don't want portfast, I want BPDU guard on it. BPDU. We should be able to do SpanningTree BPDU guard. See, portfast default on this. BPDU guard, enable or disable, we should be able to do it globally also. Again, the problem with the simulators sometimes is they don't always let you do what you want to do. So BPDU guard globally configured. It's only effective on the ports that have portfast on it. Two configuration options. Globally, SpanningTree, portfast, BPDU guard, default, and then per interface SpanningTree BPDU guard enable. I didn't put the SpanningTree, the portfast, in front of it, the BPDU guard. BPDU filter prevents specified ports from sending or receiving BPDUs by putting them into the error disabled state. We have heard the term interfaces and the port states that they go through whenever we bring a switch up, we power on. They all initially go into blocking state, then listening, learning, and forwarding. And this disabled state could be disabled state. This is for rapid. This is for per VLAN. So what I'm going to try to do is to restart one of these. Let's restart this one. Let's reload this one and see if we can see some of the port states. So first we're going to start out in blocking mode, if it will reload. Go spanning tree. We have one in listening mode and one in blocking mode when we do that. Listening and learning goes on, and we have a listen state here for the different learning. Well, we're in learning state, learning, and in a blocking. Listening, learning, and the role is a root port. It's going to the root bridge. Listening, learning, and now it's in forwarding state. IEEE. Yeah, the reason this one is so fast, this one actually has a rapid per VLAN. IEEE is the rapid. So it happened pretty fast because it had the rapid protocol on it. Let me look at one of these here and see if it has all of that too. And they all say IEEE. So when the algorithm is run, it transitions each port through the several states, and the little circle down at the bottom, the blocking 20 seconds, which stays in blocking state. Then it goes into, this is per VLAN, goes into listening state for 15 seconds, and then learning for 15 seconds. Blocking is pretty obvious. Listening is listening for topology changes. It's exchanging BPDUs. The learning state is learning the MAC addresses of the devices. And then in forwarding state, obviously, it's going to be forwarding information. And we'll see if I line to another one here, spanning tree, blocking 20 seconds, listening 15, and then forwarding. Blocking moves to listening after it decides it is a port, it is a root port or a designated port. So the link comes up after that, and then the learning process, learning the information about what is on the network. Enable STP interface always enters blocking state, and after the device initializes, it sends BPDUs to the Ethernet and or radio ports if it is a wireless access point. Access points exchange BPDUs, identifies the root access point in the network, and the interface is in a blocking state, does not participate in frame forwarding, and discards frames received on the port, does not learn addresses. The interface in blocking state will receive BPDU. So to get to 50 seconds, the 30 plus 20, that's a long time in a network. And remember, this protocol was designed so that if a port or a device or a path goes down, it'll automatically renegotiate a new one. So it's going to take about a minute, and a minute's a long time on a network. So after the blocking state, the listening state, first state after the blocking state, determines that the STP determines that the interface should participate in frame forwarding. The device enters this state. Otherwise, it will remain in the blocking state. And we've seen that the block ports are there. They're blocked. Excuse me. When the interface is in the listening state, it discards the frames received on the port. and does not learn addresses. Listening state will receive BPDUs and the default duration 15 seconds. After the listening state comes the learning state. When it's in a learning state, prepares to participate in frame forwarding. Learning state discards the frames received on the port, will learn addresses and receive BPDUs, and again the default duration 15 seconds. This is the kind of thing, just as I'm not saying that they will, but this is the kind of thing that really lends itself to drag and drop questions and things like that. Blocking, listening, learning, forwarding, and then how long are they in each of the states. And you might have one for, and we'll look at rapid, it's going to have a little bit different states, what goes on in each of these things. And in a forwarding state, at next step after the learning state, when interface is in forwarding state, participates in frame forwarding. Frame forwarding receives and forwards frames received on the port. Interface in forwarding state will learn the addresses, receive BPDUs. So, and it's going to receive, if we have any of these topology change messages, it's going to get those things. The disabled state is the next one after forwarding state. When an interface is in disabled, it doesn't participate in anything. Disabled means we gave it the shutdown command. The interface in disabled will neither learn addresses or receive BPDUs. It's going to be shut down, and it will be administratively down. Another chart here: forwarding, listening, forwarding, learning, listening, beta, disabled, blocking. Let's go from the bottom up. Disabled, administratively down. Blocking receives BPDUs. Listening, learning, and forwarding is the process that we would go to get there. Blocking, 20 seconds. Listening 15, learning 15, and then forwarding it starts with the packet forwarding. Spanning tree and rapid spanning tree, and these we really mean per VLAN spanning tree plus and per VLAN rapid spanning tree plus for these things. These are the .1Q ones. Principal operation, topology change when the port that's in the forwarding goes down. Blocking, for instance, the state changes when the port transitions to the forwarding and the bridge has a designated port. This means that the port is not standalone. The process to send a notification to all the bridges involves 2 steps. Bridge notifies the root bridge of the spanning tree, and the root bridge broadcasts floods. Let's use floods. The information into the whole network. Edge ports and port-fast enabled ports don't generate topology changes. So one of the reasons that we do want to use the edge ports, the port-fast, aside from the fact that you don't want your user sitting there trying to log on and getting frustrated for a minute or whichever one we have enabled, when they shut down a machine or bring a machine up, it's not going to generate a topology change message and result in a lot of calculations that are probably going to be they're going to be unnecessary in the topology. So the 2 different ones here, 802.1d and 802.1w, the states. Disabled is 802.1d is going to be discarding in rapid. Blocking is going to be discarding. Listening is going to be discarding. Learning is learning, and forwarding is forwarding. And then the default port status operations, all of these are enabled. Port in the active topology. In the listening state, it is in the active topology. And the port learning MAC addresses, no, yes, and then yes as we go on down. So the different states for the per VLAN and the rapid per VLAN spanning tree protocols. Another, because there's lots of different ways to look at this, and you're probably tired of hearing all of the different ways we have to talk about this, but we have a bunch of them. Transitional is a term that probably would be good to take away from these things, that the listening and the learning are transitional states that we do. Blocking is a stable state. listening and learning is transitional, and forwarding and disable are going to be stable states. And then do they forward BPDUs everything except disables, which is shutdown. Forwards user frames only when we get to forwarding, and then learns the MAC addresses. In the learning state, learns the MAC addresses, and then forwarding learns the MAC addresses. The LED colors, amber, 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 and then green when we actually get to forwarding state as it goes through the process to get to these things. Let's see. I don't think there's anything different in this one. The disable, discarding, disable, blocking, listening are all discarding for the 802.1W, the rapid per VLAN, and then is it in the active topology? Is it learning MAC addresses? Sort of arrangement. Edge ports and port fast ports, 30 seconds DHCP request, and this is again kind of the thing that I was talking about. Ours were logging in, they had to get DHCP addresses also. But how long does it take for the NIC to actually be able to get onto the network when we do these things? Edge ports, concept already well known to Cisco SpanningTree users, basically corresponds to the port fast feature of the edge ports. One of the key turned down at the bottom in red there, port fast keyword be used for edge port configuration. The Cisco implementation maintains that the port fast keyword will be used for the edge port configuration. So when we're talking about edge ports, we're really talking about port fast enabled ports. Ports directly to end stations can't create bridging loops in the network, so therefore we don't have to allow SpanningTree to go through its calculation process to see what's going to happen with these things. The edge port directly transitions. You saw that in the simulator when we configured port fast, turned it off, turned it back on, it came up immediately. No waiting for the 50 seconds for the per VLAN SpanningTree calculations, negotiations to take place. Edge ports nor port fast ports are going to generate topology changes, so there's not going to have to be any calculations with them. Another big advantage to using them. Receives a BPDU, edge port that receives a BPDU, loses its edge port status, becomes a normal SpanningTree port, goes through the negotiation process. User configured value and the operational value of the edge port state. And if we have BPDU guard, not only is it going to lose its edge port state, it's going to be put into error disable mode. So port fast, really good deal. Brings the ports up immediately on the switches. Problem is, if somebody plugged a switch in and created a loop, we could have a network crash, and that's what happens if an edge port gets a BPDU. It immediately loses its edge port status, goes into the regular SpanningTree negotiation, unless we have BPDU guard enabled, and in that case it gets put into error disable. These are the timers, and we talked about what goes on and what makes the rapid so much faster. In SpanningTree, hello time is 2 seconds, and I think that's what we saw in the Wireshark, which I just closed. And then once the port is in blocking state, it stays there for 20 seconds, then moves to listening state for 15 seconds and learning states for 15 seconds. That's where we get our 50 seconds on these things. SpanningTree, the hello time for this one is much lower, to 1 second, and then we had 2 seconds on the other one. Hello time 2 seconds. This one's configured for 1 second. A lot of this stuff is configurable so that you can speed things up. In rapid, the maximum age time is 3 times the hello. So the maximum is 6 seconds, and the spanning tree up here, 2 seconds, the 10 times the maximum age size, that's where we get the 20 seconds. So we get 16 seconds, and then moves into the learning state, which is going to be 15 seconds. So we're talking, instead of 50 seconds, about 21 seconds for the rapid convergence to take place. One of the things that happens in the rapid is it discards the MAC address table, so you get a whole lot more flooding that goes on with it than you would with the per VLAN, because it doesn't dump the MAC address table like the rapid does. Another example here, determine the root bridge of these guys, and actually take a look here for a few seconds and see if you can do the root bridge. I'll put the costs on and see if you can come up with the root bridges here. This goes from a gig to a fast, so it's going to revert to a fast Ethernet. Path cost, link speed, 4 meg, 10 meg, 100 meg. So this one's going to be a 19. This one's going to be a 19. This one's going to be a 19, and this one's going to be a 4. So take a couple minutes and see if you can come up with the root bridge and the designated ports and the root ports. I'll pause this recording while you're looking at that. The root bridge has got the lowest MAC address, right? And again, this is one of those things that if you're not given any other information, then you have to assume the defaults, and the default priority 32.768. So this is going to be the root, right? The root port, pretty straightforward after that, isn't it? That's going to be a root port because it'll be the lowest cost. That's going to be a root port. What about this guy? What about this guy? Which one's the root port? Which one's the lowest cost of the root bridge? FA02 or FA03? 03. So this will be the root port. And the root port's going to go to a designated port, and this will be designated port and a designated port. Now on this guy, which one has the lowest MAC address? And you have to go a little bit farther on this one. So this is going to be the highest, right? 1C is higher than 1B. So this one should be, I think, let's see, that would be 38. That doesn't matter. That one's going to be, we're looking at which one's going to be the block port here, aren't we? I think that maybe that one's going to be the, yeah, let's don't do that. That one's not going to be, we're going to have the, this thing here. And maybe this one will be the block port on this segment here. And I got rid of a lot more stuff than I wanted to, didn't I? This was the root bridge. A root bridge, and this was a root port. And this was a root port. And this was a root port, and this was what, 4, 19, 19, and 19. And so this one here is going to be the block, the highest one. The highest one's going to be the blocked 1C, higher the lower win. So this would be a forwarding port here that goes around through the system. The answers here: root port, we got the forwarding, the block, the root, and the cost of 4, 19, 19, 19 to get our loop-free topology in these things. the step-by-steps to do this. Configure terminal, spanning tree, mode, per VLAN, and to go from I can't do multiple spanning tree in Packet Tracer, but we can do the rapid to go from one to the other. If I go into here and drag up a switch and wait for it to start up, and it should have spanning tree enabled on it by default. Show spanning tree, no instances running. Okay, so let's do. It should have it running by default. Config T, spanning tree. Let's see, VLAN 1. Now it's still not doing any. You know why it's not? You know why it doesn't have any instances? Doesn't need any instances, does it? Probably better off doing one of the others. I really would be better off doing one of the others. Okay, so we can turn these on. We can go up here and look at these things maybe real quickly because they are connected to other devices. If it's all edge ports, show spanning tree. So this one RSTP, if it's rapid spanning tree protocol, this rapid per VLAN spanning tree protocol. In order to do that, let's do the config. Let's change back. Config T, spanning tree, mode, per VLAN, do, show, spanning tree, and then IEEE is going to be the per VLAN spanning tree protocol. I think I said those backwards a little earlier, but per VLAN. And if I go into it and use a spanning tree mode rapid, the do show spanning tree is going to be RSTP, rapid spanning tree protocol, and it's going to be the one that is going to converge much faster. This one's in learning after we changed it, and if we go back, it's in forwarding already. So it was just really just the few seconds that were required for that. So to change the modes, and again in this I can't do a multiple on this one. The only two modes I think that it gives me, unless they have updated it. Let's see. Spanning tree mode, and this just gives me per VLAN and rapid per VLAN to configure on Packet Tracer. So we can change these things, show the spanning tree summary, show the spanning tree interface ID to verify the configuration, the copy run start, or use copy run start to save the configuration files, the show commands, and hopefully as we've gone through this thing, we've done some of those already. The next thing is kind of jumps into something that we'll talk about a little bit tomorrow, switch stacks. And what a switch stack does is combines switches into one virtual switch, and that's what the stuff on the back, it's a ring type arrangement where stackable switches, configurable stackable switches, not ones that can be stacked on each other, but switches that can be configured for stacking, are combined together as a single point of management. So in this one, instead of having 1, 2, 3, 4 individual switches to manage, we manage all the switches as an individual entity. A lot of things going on to try to automate or to centralize management of what happens for these things. And this for spanning tree itself, and again tomorrow have a few slides on the switch stacks, or stacking switches. Yeah, switch stacks. Every stack member runs its own spanning tree, and to the rest of the network, the entire stack appears as a single switch. When you have more VLANs defined than instances of spanning tree, you configure it a per VLAN plus or rapid only on 128 VLANs on each switch stack. And again, to me, that's still a lot. Maybe it's just me, but that's quite a few VLANs. Be able to operate the remaining only with spanning tree disabled. And you saw that spanning tree disabled is really not something that we want to do. Keep in mind that an alternative here might be the multiple spanning tree protocol. We'll be able to use MSTP to map multiple VLANs to the same instances of spanning tree. When you already have 128 instances in use and require STP on one of the VLANs, need to disable a spanning tree on another VLAN in order to do that. So it is a zero-sum game is what they're all saying. That we have so many instances of spanning tree that we can use on these things, and that's all that there are. Can use the spanning tree commands to control the configuration of it, be able to configure the switch and port parameters before creating the spanning tree in the ports instance. And when a spanning tree instance is created, these switches and port parameters are going to be applied. A switch may support per VLAN plus rapid and multiple spanning tree. Only one version can be active at a time. I was going to say instance, but within a version, within rapid per VLAN, we have different instances, the numbers, the different spanning trees that are running at the same time. The same spanning tree version's got to be running on all of the stack members when we have this configuration. This is, and I'm just going to go over. This is another one. Shows spanning tree interface detail. You can see the kind of information that you have. There are, I think, a couple of things in here that maybe I haven't talked about that might come up. Let's see, the port cost we got, port priority, the default port priority is 128. This is something else that is configurable. And if we have multiple ports, we have ports 1, 2, 3, and so on. Each of them is 128.1, 128.2, 3, 4, and on down the line. The lowest is going to win. The lowest priority, the default priority for all of them is 128. So therefore, the lowest port number will win if all other things are equal. Let's see, the designated route has a priority 32.769. Designated bridge has a priority 32.769, and it has a different address. The forward delay and the things that are going on, the configurations that are going on, you can see, and this is in the show interfaces of these devices. The next thing that occurs in this is 15, 30, it's a little over an hour. 15, 30, 45, 65, a little over an hour's worth of labs. And there's a few more slides, but I'm going to go ahead and take a break, come back at 10 past, and we'll finish these up, and then you can do labs for the rest of the day. Questions, comments? This is running on a virtual machine in GNS3, which is running on iOS on a Windows machine. But you get an idea of how frequently these things go. We have the cost here. Some are 0, some are 4. The costs, we've got a cost of 4 here. Capture that one in there real quick, and let's see what we can see here. We have the maximum age 20 seconds, the hello time 2 seconds, the forward delay 15 seconds, which is the per VLAN arrangements, I believe. Route path cost is 4 on this one. So it's a gigabit. They're all gigabit connections that go through these things. And the root identifier that goes on the BPDU flags. Again, the topology change acknowledgement and topology change, both of those are no's on it. Let's see, BPDU type, protocol, version, spanning tree 0. So this is per VLAN spanning tree. Now let's see if I can now get it back off of the screen or not. And get it out of the way. So the last few slides of this initial troubleshooting STP checklist, the spanning tree, what's going on? Spanning tree is not doing what we think it should do. It's not disabling the ports or blocking the ports that we think should be done. So before you start with the actual troubleshooting, more information about the network layout, the details, the existing STP configuration. Is spanning tree configured? Which version of spanning tree is configured? Have we modified, or has somebody modified the root ports for the root bridges for any of the VLANs? So the actual topology diagram. What is the physical layout? What's the actual physical layout that we have? The diagram for it, and what would you expect with that? Interconnector ports of the devices, STP configuration details, which is going to be the root switch. And yeah, I know it'll calculate it, but sometimes you want to sit down and see what it's going to be, do your own calculation. And you've seen in a couple of them that, yeah, you can actually get there on the calculation. Or we can just go in and specify the root bridge. We didn't do that yet, did we? Let's do that on one of these just for the heck of it, because it's not that one probably isn't the root bridge, right? Because it has one of the ports disabled on it. Locked. Spanning tree. And then we're going to go in here and do VLAN. And let's do VLAN 1. And let's just make it the root bridge for VLAN 1. Yeah, root, primary, secondary, yeah, primary. Do show VLAN, and VLAN, do show spanning tree. And we're listening, we're going around and around and around. This bridge is root, so we should be going through, and we are going through some calculations here, so that these guys, this one remembered was the block port, so something else is going to have to come up as the block port. But we can specify by that command which of the devices that we want to be the root bridge. And you can, if you have multiple ports, you can modify the priorities of the ports. Again, they're all 128. You can change the port priority too. Initial, consider the following: the type of spanning tree configured on your device, and per VLAN rapid and multiple. How many instances do we have running? The network topology, including the interconnected ports, identify all the redundant paths of the network. Show spanning tree summary totals command to verify the total number of logical interfaces in the active state are less than the maximum allowed. And we talked a little bit, where there was a slide that talked about what are the maximum numbers that you can have, and that's like everything else. That's something that, not everything else, but something that's going to change based upon the hardware. Verify the primary and secondary root bridge and any configured Cisco extensions. The primary bridge and the secondary bridge. Secondary bridge is going to take over if the primary fails, and they do call them bridges, root bridge, even though we are using switches. Show the show running config spanning tree. Actually, let me go back to this guy. Let's just see if we get anything different than we would have gotten with Packet Tracer, because get rid of this. Stop and quit without saving. These are actually supposedly layer 3 switches. So let's try some of those commands on it. And I think that this is, I found this the other day. Layer 3 switch configuration in GNS3 is usually not supported. This actually is a virtual machine. So I'll just look and see what some of these things that might not be available. So show running config, show running config spanning tree, and I love it when it doesn't work. I think it's supposed to be piped in there. Show running config, and maybe these are ones that I'm not very good at. It's still, well, we won't do that one. So let's try the show.
You got to put begin after the pipe.
Yeah, that's what yeah, you're right. Begin after the pipe, right? Pipe and then begin, right?
Yep.
Told you I'm not very good with those. I always screw that up. VLAN internal allocation, VLAN 100, and we have VLAN 200, 300. There are a couple of VLANs obviously running on this one. Negotiation auto that goes on around. This is at least a kind of a Cisco. This is actually a simulated Cisco iOS that this thing uses. Let me make this maybe where you can see it, not see it, so I don't get away with the other thing down there. But show spanning tree detail. Port 1 is a route forwarding designated port priority and all that other good stuff. So the detail that you can see in these things, and it's going to be on a per port basis. Unfortunately, I didn't put a whole lot of ports on this thing. Get out of that. Show spanning tree bridge. The VLAN, IEEE, these are all going to be per VLAN. The bridge ID 32768, and this is for the VLAN, the bridge ID and the VLAN 32768, VLAN 100, 200. So it is the same on all of these things. I don't have a multiple spanning tree running on it, support and the rest of those things, but just some of the detail that you can get with something like a GNS3 that you can't get in Packet Tracer. The data loops, what's going to be the indication? The biggest indication is your network's going to slow down to a crawl, slow down to a stop. High utilization of the links up to 100%, high CPU utilization, constant relearning and flapping of the MAC addresses, and you'd have to use the show MAC address table or a debug command in order to do that. Excessive drops of the output interface. So we've got the traffic that is just regenerating, kind of like I tried to show early in the packet tracer that goes on. Excessive packet flooding, unstable topologies trigger excessive flooding. The rapid, when the port state is changed to forwarding or as a roles designated route topology change is initiated. So the topology change is triggered, port state changed, disconnect something, put something on it. The reason we want edge ports is they don't trigger topology changes. And the rapid per VLAN spanning tree flushes the MAC address table when it gets a topology change, shortens the aging time. That says here that the immediate flushing of the forwarding table restores connectivity faster, but it's going to be more flooding. It should be, I think, more flooding. No, flooding should be, and I'm getting flooding and broadcast going in my head, but more flooding is going to happen. Link flaps cause topology change, so continuous link flap, a link going up, coming down, or flapping up and down can cause these things, repetitive topology changes, and flooding, more traffic, topology changes. You saw in the STP, Wireshark that was there a topology change or not, what happened for these things. Slows the network performance, causes packet drops, and flooding is always going to be something that's going to take some time because it means that we have unknown MAC addresses. The more topology changes that we have in the rapid, the more flooding is going to happen because we're going to flush the MAC address table to get there. Convergence time issues, and the reason this image is here is the how big, what is the radius of the network, and can take longer than expected if there is a different network topology than was expected. Errors in the documented topology diagram, and those are easy to get. Most of, maybe just me, but many of us, I won't say most of us, many of us are not real good at documentation. And that's one of the things that really can kill you. Misconfiguration of the timers, the diameter, 7 hops of spanning tree is supposed to be the maximum that we have, 7 switches away maximum diameter for each of the instances. Bridge assurance, root guard, BPDU guard are all things that can affect what goes on. BPDU guard, we saw, is just going to put the port into air disabled state. Overloaded CPU during convergence exceeds the recommended logical port VLAN limit, and then software defects that affect spanning tree. Spanning tree is not the perfect protocol, and people have talked about, and I've read about that, yeah, they had some real issues with it. And some people don't want to use it. We had spanning tree running. We didn't really have any issues, but we didn't really have a lot of loops that physical loops that were created in order to have a redundant, resilient topology in the system. Number of features, enhancements to protect the networks, troubleshooting, to isolate, find the cause of a particular failure. With the implementations of the enhancements, the only way to secure against forwarding loops. Auto negotiation mechanisms can convey remote fault information. Quickest way to detect failures on the remote side. If failures are detected at the remote side, the local side brings down the link even if the link is still receiving pulses. And forwarding loops going to happen here, receiving pulses. A number of things happen. It can happen if we have fiber because of the two fibers that come into the situations. Forwarding loops, and I put the image down here, what is an ether channel, because it talks about those LACP, link aggregation control protocol. The guidelines for troubleshooting forwarding loops, and this is the UDLD, the unidirectional link detection on all of the switch-to-switch links. This is something that is much more likely to happen on fiber than anything else because of the two fibers, one transmit and one receive. If you lost the receive and the transmit is still working, you're transmitting but you're not receiving. So what this enhancement does is detect the misappropriation, not the word, but misconfiguration, alignment of the hardware. Bridge assurance feature configuring all the switch-to-switch links as a spanning tree port type. Ensure that you enable the bridge assurance feature on both sides of the links, and that's we do have to, in many cases, configure both sides. Spanning tree, we kind of get used to. Oh yeah, we can do a negotiation. It negotiates and it automatically starts things up. Some of these other things, the UDLD, don't do those. Don't do negotiations. They have to be configured on both sides of the link itself. Set the edge port to limit the amount of topology change notices, the number of change notices, because the edge ports don't generate topology changes. And down here, enable the link aggregation control protocol for port channels to avoid port channel misconfiguration issues. We'll do ether channel port channels tomorrow. LACP is the standard. Cisco has its own proprietary PAGP. If you have, and they always recommend, if you have an all Cisco environment, that you use the Cisco protocol instead of the standards for those things. But an ether channel is something where we combine a number of physical links into a single logical link for a high-speed connection. Don't disable auto negotiate on the switch links, and we looked at some of the issues that can happen, the little demos in the troubleshooting on Friday, that if we have them configured in properly. And auto negotiation, probably the best bet for all of these things. Auto negotiate issues, not really. There really haven't been any. Maybe somebody knows about some, but I don't know about any for a number of years. Set up all the end stations as a spanning tree edge type port, and we want to do that. The summary, and this one is one that you really probably do want to poke your eyes out after you get done with it, but spanning tree 802.1d layer 2 link management protocol prevents loops, so that prevents logical loops, so we can have physical loops, and we get a break in the looping with block ports, so that we have backups readily available if a link goes down. 3 STP modes supports the newer Cisco switches per VLAN plus rapid per VLAN and multiple spanning tree. The default is per VLAN. BPDU guard that balances the functionality of port fast. Port fast disables spanning tree and allows the ports to come up immediately. BPDU guard, it configures the port such that if it gets a BPDU, it will immediately put the port into air disable mode, shut it down basically. The port states were blocking, listening, learning, forwarding, and we had different timings on whether it was per VLAN or rapid per VLAN. The rapid per VLAN wound up being like 21 seconds, where per VLAN is about 50 seconds, where the blocking is 20, listening 15, learning 15. And then we go into forwarding. Radio and Ethernet interfaces and the native VLAN on the access points are all assigned to bridge group 1 by default. We can change the native VLAN. We looked at how to do that. If we do change the native VLAN, that's one of those that's got to be manually changed on both sides of the trunk port, otherwise we'll get a native VLAN mismatch. iOS commands need to be executed in privilege exec mode to display the status of spanning tree, and the convergence can take longer than expected if we have a topology, an unexpected final topology. The topology is not what we thought it would be. Data loops, common problems, are a common problem in STP networks. So, and the data loops that they were talking about was here. If we have data loops, and hopefully when we have STP configured, we won't have data loops. We're going to have high utilization, and really the network, or at least our network, got totally shut down whenever we had our little loop. Questions, comments? I don't think I really want to start the next one unless you do, because we don't have a lot of time after you get done with the labs.